Hi, I'm Gord. I'm the designer of board games like Santorini and puzzles like you'll find in this video series that's sponsored by MCATA, Math Council, Alberta Teachers Association. Today, we're going to look at what taxi cab drivers do all the time. They drive people from one address to another address. Here we have two addresses. We're going to drive between them. Here's a possible road. Is this road a good road? Well, let's look. The prime factorization of 60 is 2, 2, 3, and 5, and at 45, 3, 3, and 5. And we look at the common factorizations. We see that there's the common prime numbers. There's a 3 and a 5 in each. And by pure coincidence, there is a road segment here that is of length 3 and a road segment that is of length 5. Is that a coincidence? No, no, it's not. So that's what we're going to be doing today. All of our connections are going to follow this pattern. We can try it with something much more difficult here. Here's the prime factorization. Why don't you stop the video? Try to connect these two using the common, I guess everything's common there except the 3 and the 2. So try to connect them, see how you can do. And here's one solution using a bridge. Here's another solution that doesn't use a bridge. Both are okay. Okay, let's see a solution for this. There we go. And another one with a bridge. Here's another one and another one. There's lots of solutions for these. There we go. Lots. But for the whole time, what is much more interesting are these triangles. I'm going to call these taxi cab triangles. It doesn't look like a triangle, but for taxi cab drivers, of course, this is a triangle. Okay. But does this work? So take a moment, make sure that every road between every pair works. The 12 and 20 work because they share a common prime factor of 2 and 2. The 12 and 30 work because they share a common prime factor of 2 and 3. But the 20 and 30, that doesn't work. Why not? Well, it shares a common prime factor of 5, but also of 2. And where's the road of length 2 between the 20 and 30? So this is a failure. That doesn't work. We're also going to say that it's a failure if you have a road going on top of another road. So this doesn't work. You can't go into the 60 and then come out of the 60 again. That's boring. Who wants to do that if you're a taxi driver? You just want to go in a nice loop. So we're also going to say that that's not allowed. Okay, here is another solution, and this one is a totally viable solution. Here's another. So these are looking like they're quite reasonably, they're not too hard to come up with, not too easy. So you could maybe stop the video now and just experiment. Try to come up with some triangles yourself, taxi cab triangles. Here's one that I found, and the question is, for every set of 3 integers that uses a bridge, like this one, is it also possible using those 3 same addresses or integers, is it still possible to make it, but without using bridges? Let's say in a different city, you have those three integers, those 3 addresses, maybe in different locations, but you find a way to connect them that does not use a bridge. And in this case, the answer is yes. Are you ready? Here, this is how you could connect them without using a bridge. I don't know if this is always possible. If you can come up with a solution that uses a bridge, can you always find a solution that doesn't use a bridge? I don't know. Are there an infinite number of taxi cab triangles? Yes, and that might be kind of intuitive, but to prove it is not totally intuitive. But here is a fun way to prove that there's an infinite number. We're going to use the number 6, and we're going to connect it left and right. And maybe you want to just take a pause here. Any of you who are out there who want to get into a proof, think of how can this diagram help us? Well, the 2 verticals of this diagram right now are length 5 prime numbers, but we could make those length 7 we could make those length 11, length 13, length 17, length 19, 23, whatever. We can increase those two verticals to any prime number. And we know that there's an infinite number of prime numbers. Therefore, we know that there are an infinite number of these triangles, these taxicab triangles that have the number 6 in them. Like, who would have thought that? This came as a surprise. Okay. Just like there are equilateral triangles, are there taxicab triangles that use the same number 3 times? Go ahead, try to solve this. Yeah, I'm going to tell you, I have found one, maybe more than one. Okay, so ready? Here's the smallest answer. I don't think that you can get any smaller and find a solution. I think not. So there is 16. And indeed, any number more than 1 that you raise to the 4th power, I think any number, I think all of those are going to work. Here is 36. This also works. And next, I have not found 4 integers whose 6 roads to one another are all working. So you can imagine 6 destinations in your city. And you can imagine a road going between every 2 of them. So these 2 and these 2 and these 2 and these 2. So there's 6 possible roads. They all have to work. I haven't found a solution for that yet. I don't even know if that's a tough problem, an extremely tough problem, a murderously tough problem, or if it's impossible. I don't think it's going to be impossible. My intuition is that this is going to be possible. So if you find it, I want to find what's the solution that has the smallest possible biggest number. Okay, I don't know the answer. Right. Where did this come from? So this came from an idea. I was trying to work with something using place value with younger kids. So here, this is where this idea came from. I was trying to think of, okay, 408 tens and 1 unit. So I was looking at these spirals, but I wasn't really happy with what I found there. But the problem that we have today with these taxicab triangles, I'm happy with that. It means that I don't know the solutions to so many questions. That's what makes me happy. Take care. Talk to you next week. Bye-bye.